In Chapter 16, we learned how to calculate the pH of a weak acid. So, for example, if I said calculate the pH of 0.10 molar acetic acid, y'all would recognize that as a weak acid. And you would know to write Ka is equal to x squared divided by initial concentration. And then solve for x, and that's your hydrogen, and find the pH, right? Got that down pat. And if you'll remember how we came up with that expression, Ka is equal to x squared divided by initial concentration, is I started out writing out how these acids dissociate. Right? And so we would write an equilibrium reaction, and we would look at what we're given in this problem, and we set up an ice table. And we said, okay, well, if I start with 0.1 molar of this, I know X ionizes, and so I know that I end up with 0.1 minus X, and I know that I start off with none of these, and so I'm going to make X. Remember? And we saw that every time it went to that, and that's how we came up with that expression. Now, do you guys remember Le Chatelier's principle? You heard that name before. Let me kind of jog your memory. Le Chatelier's principle said that if a system at equilibrium, that system right there, if a stress is applied to the system at equilibrium, the system responds to relieve the stress. So in other words, if this is at equilibrium, if I added one of the products, then that's a stress to the system. Like if I added more hydrogen ions to it, that would be a stress, and this system would respond to shift back to the reactant side. Likewise, if I added more of the acetate ions, and you guys recognize this, CH3COO, that's the conjugate base of the acetic acid, right? Because to get to the conjugate base, you just take a hydrogen off the acid, and you've got its conjugate base. So if I added more of this, that would make the equilibrium shift back to the left. In turn, that's going to affect how much hydrogen is there and hence affect the pH, isn't it? Okay. So what if I kind of added to the question that I have, and instead of just saying calculate the pH of 0.1 molar acetic acid, well, 0.1 molar acetic acid, that implies that it's just in pure water. And so the only thing really that's there that's going to affect the pH is the acetic acid. But what if I said calculate the pH of 0.1 molar acetic acid in 0.10 molar sodium acetate?
Is this still chapter 16 or 17?
This is chapter 17. When I add that information to the problem, what it actually does is it changes the setup of that ice table. No longer am I starting out with 0 acetate, because now I'm putting acetic acid in a solution of sodium acetate. So do you see that acetate in this example would be a common ion? Okay, that's a term that you might see some. Chapter 17 starts off talking about an effect called the common ion effect. In this example, since I'm putting acetic acid, and I know this is how it ionizes, in sodium acetate, for this one, the acetate is the common ion. So how that changes the ice table, right here, instead of having 0 acetate, now I'm actually also starting off with 0.10 molar acetate. So no longer do I have 0 of it because it's not going in water. Now I've got 0.1 molar of the common ion.
What about the sodium part?
The sodium is a spectator. The sodium, would sodium have an effect on pH? No, because it's a group 1 metal, no effect on pH. So see, the sodium's not going to matter. Yes. I had to look. Sometimes I forget to hit record. Yes. Okay, so it changes the ice table. Guys, what you actually have when you take acetic acid and sodium acetate in this example, I went ahead and wrote common ion because that's a term you're going to see as well, and I don't want you to think, whoa, she never said common ion. But for this example, when I put it in sodium acetate, do you see Le Chatelier's principle says that when it was just plain old acetic acid, this is going to break down, right? The acetic acid would break down. But when I put it in sodium acetate, not as much is going to break down. Because essentially what this is doing is stressing the equilibrium. And since I'm adding product, acetate, it's causing the equilibrium to go back to the reactant side just a little bit. It is a Le Chatelier concept. What you have here is actually a buffer. Y'all have heard of a buffer before. What does a buffer do? Chemistry, biology. What's that? Not the rate. That's catalyst. Catalysts are going to affect the rate. What's that? That's catalyst.
Is it more neutral?
Not necessarily. It doesn't have to be neutral. Okay, what a buffer does, y'all, a buffer solution resists a pH change. Buffers help maintain pH. You've heard of that before? Biology? What we have here is a buffer system. How do you know it's a buffer? Well, for us, a buffer will consist of a weak acid and its conjugate base. Therefore, that can be a buffered system. Or it will consist of a weak base and its conjugate acid. And we're going to stick to those simple buffer systems for what we're doing in here. In this system, we have a weak acid, acetic acid, and we have its conjugate base, sodium acetate. It's actually really easy to calculate the pH for a buffer. And what you will use is an equation known as the Henderson-Hasselbalch equation. Have any of you guys heard of that? And I kind of didn't think so because it's introduced in biochemistry, and y'all haven't had that because you're in Chem 2 now. The Henderson-Hasselbalch equation looks like this. The pH is equal to the pKa plus the log of the concentration of the base divided by the concentration of the acid. Y'all know what pH is, right? pH is a measure of the hydrogen ion concentration, and we know below 7 acidic, above 7 basic, etc., etc. What's a pKa? Well, do you know what a Ka is? Yes. What's a Ka? Y'all said yes.
Concentration of weak acid.
Ka is an acid dissociation constant for a weak acid, right? Products over reactants. Where do you come up with a Ka? Where do you find those? There's a table. So the pKa, y'all, it's just the negative log of the Ka. Very simply. If you look up the Ka, you can look up the pKa. What's log? Well, it's on your calculator. It's a function. The concentration of the base, that around B, that means concentration of base, and the brackets around A means concentration of the acid. So we can use this formula to calculate the pH of a buffer. Let's do that. Calculate the pH of 0.1 molar acetic acid in 0.1 molar sodium acetate. Okay, so the first thing you have to do is you have to look up the Ka. And obviously it's the Ka for acetic acid because that's the acid. And that is 1.8 times 10 to the minus 5. Is that right? And we look that up just in the table in the book. You don't memorize those, you look them up.
So you'll get the book on test. That's what I heard.
I think I'll make a copy of a table for y'all. That will work better. So so I look up the Ka, or maybe I'll just write it in there with a problem. The Ka for acetic acid is, yeah? Maybe. Just let you use the book. The negative log of that gives me the pKa. So the pKa is 4.74. Stop me if you're like, whoa, what'd you do? The negative log of 1.8 times 10 to the minus 5 is the pKa. Yes. Now I plug it into Henderson-Hasselbalch. So the pH is equal to 4.74 plus the log of, what up there in the problem's the base?
Acetate.
The sodium acetate is the base, divided by the concentration of the acid, which is the acetic acid.
Okay, I thought, so the B is for base, A is for acid.
Yes.
I thought it was B for product.
No, B is for base and A is for acid. Yeah, that's important. On this one it didn't matter because they were both the same. But 0.1 divided by 0.1, Kelsey said that's 1. Can't I just take the log of 1? Yeah. The log of 1 is 0, and so the pH is equal to 4.74. No, it will not always work out that way.
I wish it did.
Calculate the pH of a solution that is 0.34 molar HF and 0.29 molar KF. Y'all take a second and work that one. I intentionally, when I read this one, I'd said HF and KF to see and show you guys that you know how to pick out the acid, even if I don't say hydrofluoric acid, right? You knew HF was the acid because it's got a hydrogen. The other thing, KF, doesn't. So here's the acid. This is the conjugate base. When I look up the Ka for HF, it's 7.1 times 10 to the minus 4. The pKa, which is the negative log of that, is basically 3.15, right? And so then I plug that into Henderson-Hasselbach. So the 0.29 is the base, 0.34 is the acid, and I solve and get 3.08 for my pH.
Yeah, this